so we are recording now, and the logistics for the exam are that it is on the friction bit at the end of chapter 4, as well as all of chapters 5, 6, and 7. And so we're going to go through each of those a little bit. It's going to be very similar to the last exam in structure as far as the number of questions, maybe a little less, or just maybe a little bit more straightforward for some of them. But no work required questions will be multiple choice, and it's just all credit based on if you get the question right or not. And then there are calculation-based ones where it is how much of the calculation did you get correct. You get partial credit for that. There will be a bonus of 5 points, and that is the main things. You can have a cheat sheet. Hopefully, after the first exam, you have a little bit of a better idea what you would want to have on your cheat sheet. But I've given some ideas out about that, so I'm going to just give them out here too by just adding a page for all of this. So the actual equation sheet that will be given is the same one that's on these practice exams. These right here. And so those you will have on the actual exam, or this sheet you will have on the actual exam. So it's more important not to write down every single equation you can find, every single example you can find in the notes. It's best to know what these equations mean. For instance, if you don't know what you're looking at right here, it's not useful to you, obviously, because you don't know what it is. This is Newton's first law. It says if the acceleration on something is 0, the net force on it must be 0. This is Newton's second law for when things are accelerating. This is the third law. This is how you can calculate weight from mass. This tells you about static friction, kinetic friction, and so on and so forth. So it's more important to know what these are saying than know what they are, because they're given. And if you know what they're saying, you'll know when it's probably likely you'll need to use a certain one. So the exam is also in order, or will be in order. They always are. So that means that if you're early on in the exam, you will probably be looking at a chapter 4, chapter 5 type question. If you're later on, you might be looking at a chapter 6, chapter 7. And that can help you know what to look for. But just reading the problems, you'll get a sense of what concepts are relevant. So, for instance, this one, I see something going around in a circular arc, and so that screams chapter 5 to me. If I see something going up or down a hill or some kind of strange looking path that I know Newton's laws would be painful for, I would think chapter 6 and conservation of energy. If I see things colliding, that sounds like chapter 7, conservation of momentum to me. And if I know what each of these equations up here is saying, I know which ones could be relevant for the problem. So on your cheat sheet, you may want to say some things about like which equations are kind of useful when. As far as examples, if you just write down every possible example you can squeeze on there, you're going to be looking for the perfect example of the entire exam, and you're going to run out of time. So don't let the cheat sheet be the thing that keeps you from getting this whole thing done. Instead, let it remind you of what you should do for certain problems. So for Newton's laws, I've tried to be pretty consistent about having that table thing. You draw a picture, you draw a free body diagram, you draw a table with the X and Y components, you add the X and Y components, you get the net force in the X and Y directions, set them equals the mass times acceleration in the X and Y directions, so on and so forth. It's the same process every time. So just follow that process. If you feel like it's a lot of steps to remember, write them down on your cheat sheet. It's more important to understand the process of solving problems and have specific problems to look at as you do this. Because if you're looking at specific problems, another thing that's going to steer you wrong is you're going to write down what that problem said about a certain scenario. And it might be different from what the problem on the exam says. Unless you're very comfortable with that fact and know when to have certain terms in these equations, when not to, don't do that. just follow the actual process of filling in that table, write that down. And you could give one example that says it's like this, but don't let examples be what you rely on to put anything to the paper. Last bit of advice as far as that goes is there are so few pictures that show up on exams, and it's a thing just in starting to learn physics of for some reason not drawing things out, seeing what's happening. So do that. Let that be your first step on any problem. If you don't know where to start, draw a picture. If you do know where to start, still draw a picture because it will help guide you through the rest of the problem. If you don't do that, you're kind of just grasping for a certain equation or writing a couple of symbols and things down, and you don't really know what you're looking for. A picture connects the dots a little bit better than some of the equations do, especially when you're not super comfortable with the equation still. Okay, so with that, let me jump to the actual notes and say what is a priority. I guess I never wrote anything down up here. Whoops. But we will be talking or asking questions about friction, so it's still important to be able to apply Newton's laws. This is that thing of draw a picture, draw a free body diagram, put stuff on axes, draw a table, all that. But applied to static and kinetic friction. So I'm just going to jump down to these examples are good examples of that. The kinematic stuff at the end, since that's more exam one, is not as much of a priority. So really I should scribble that and not circle it. That's not as much of a priority as just this force related stuff and accelerations. And do you know if something is or is not accelerating? Those types of ideas. But you can still get to those answers with nothing but the same process we've used for any types of forces, as well as the behavior of friction. Kinetic friction is proportional to the normal force through this coefficient of friction. Maximum static friction is as well through a different coefficient of static friction. But static friction is a little bit more interesting in that it can change depending on the applied force up into a point. You pull harder and harder and harder on something, friction can pull harder and harder and harder back until it reaches its maximum value, at which point you cannot pull any harder without getting the thing to start moving, getting the block to move in this case. Call that the breakaway point, and that's where static gives over to kinetic friction. So most important things so far are not that, but applying Newton's laws, the behavior of static friction, and this as well, that box thing, the behavior of kinetic friction is all summarized in those equations. But how we got to those is by looking at, observing the behavior of friction. So it's good to know what these equations are saying in terms of that as well. The direction of friction is not something that's a heavy concern of mine, but I will say that the important thing about it is it's opposing relative motion between two things. And so for walking, the relative motion is between our foot and the ground. And it is the motion that would occur were friction not there, which is the motion that occurs more or less when we're walking on ice. Our feet slip. So that's what makes the direction of friction a little bit odd during walking is it's always opposing which way our foot would slip if we were walking on ice. It's not a big concern for the exam, but it is something worth pointing out. Okay, so I said those examples are good. Then we're on to chapter 5. You don't need to know how we derive centripetal acceleration. It is good to know this stuff, this velocity thing, right? It trips everyone up every time, and for good reason. It's subtle. Velocity is not constant during uniform circular motion because direction is changing at all times for something moving in a circle. The rate something moves around in a circle, the speed, is constant in uniform circular motion. It's just the direction that goes with that speed to make up the velocity. That direction changes, so the velocity changes, even though the speed is constant. And direction of centripetal acceleration is important. It's the thing that keeps deflecting something so that it stays on a circular path rather than going the way it wants to go due to its inertia, which is a straight line. So the direction, centrifugal acceleration, and its size are important things. So this example is a good one for both things because we labeled the picture. Centripetal force. Size and direction are important again. It's towards the center of the circular path. It is the force that makes something continue moving in a circle. As far as the different types we've looked at several. If I were to look at these specific examples like we did in class, the ones I would focus on are the gravity one for satellites and then just something on a string. Don't worry about friction being the centripetal force. We already did enough with friction for chapter 4, or will have enough of it on the exam. So this right here is a good example because it is applying Newton's laws, still using the tables, but now for the case of a centripetal acceleration, where we have to worry about that v squared over r thing and also get the direction correct by looking at our picture and saying, is it in the positive or negative direction? So I said that the gravitational one, the satellites, would be a relevant one. When I say that, I don't mean the period of an orbit. I'm going to say don't worry about that because it's a little bit algebraically messy. I would be more worried about things like orbital speed, or again, could you find centripetal acceleration of something if you know its orbital speed, you know its radius that it's orbiting in. That's more what I'm looking for. So you could be asked to apply this equation. It will be given, but you should know when it should be relevant, which is when you're given information about the mass of the thing being orbited. You're given information about the radius of the orbit. You want to find the speed, or you're given any two of those things and you want to find the third. This was just because it was right before break to talk about that projectile motion is like a less extreme version of satellite motion, and then escape speed is a more extreme version. So it's all kind of on this continuous spectrum of launching things from something falling straight down all the way to it escapes our entire solar system or galaxy if it has enough speed. This example is out. This example is good insofar as it's still just applying this process. It just happens to be applying it to friction. So it's good for practicing getting used to centripetal force and how you deal with it, but we're not worried about friction specifically. Exam problems, chapter 4, 4, 6, chapter 5, 13, 16. Yes, I will go over some of those, or however many we are able to get to by about, I'll say I'll cut off at around 6:15, 6:20. So yes, I will do that, Kennedy.
Thank you.
Yes. Okay, so banked curves are out for the exam. This whole page, not a concern. Again, another thing of here's something cool, but you don't have to worry about ever again, but I just thought I'd mention it. Okay, chapter 6. The big things are we use this money analogy. If it helps, great. If it doesn't, don't worry about it. So marking it out as far as if the money thing never made it make any more sense, don't rely on an analogy that doesn't make sense to explain something else that doesn't make sense. Just take more focus on the work and energy concept itself. So for work, the important thing is the stuff we've said here. That changes in speed indicate something to us about the work done. And if we're being extra specific, now that we know a little bit more, it's the net work that actually determines that change in speed. So it would be, if you see something speed up, you know positive net work has been done. If you see it slow down, you see negative work has been done. If there is no change in speed, zero work has been done. That can be because something's moving in a straight line at constant speed, moving in uniform circular motion, or not moving at all. Any of those indicate zero net work done. Or if you're talking about a specific force out of that overall net force, for instance, the normal force, that can do zero net work because it's perpendicular to the displacement of something. This equation is an important one, but usually when combined with, maybe in a two-part question, the work energy theorem. So when combined with this right here, you would find the work done by all forces by calculating the work done by each and adding them up, which is what this thing says. And then that will tell you the change in kinetic energy of something. This example right here, that can be applied. So we found the work done by each force, the one the man exerts and the one gravity exerts, found the network by adding them, and that tells us about the change in kinetic energy of the barbell. It is no change. And so it would make sense it's moving at constant velocity as the problem states. Okay. So definition of work, definitions in general are also a good thing to write down in case you forget what is kinetic energy, what is work. You don't need the derivation of it. So an example like this, where it's like a satellite, is not specifically important. Probably this version, this calculation of it would be a more relevant thing to consider. But the idea of perpendicular force and displacement means zero work. And then these angles less than or more than 90 mean positive or negative. That is a good concept thing, good conceptual thing. But it's summarized here. Positive network increases kinetic energy, negative decreases, zero doesn't change it. Gravitational potential energy will show up, as far as I can think of, only in terms of conservation of energy. So we had to build up a little bit more gradually to conservation by doing some practice with gravitational potential energy and work energy theorem. But if you're seeing potential energy show up, it's good to know that it does the opposite of what kinetic energy does when something is rolling down a hill, being thrown, whatever. But it will show up not in terms of this stuff down here, and not like the work done by gravity. The only tip is this thing down here that you usually want to call the lowest point in a problem zero height. If it doesn't give a height for it, just call it zero. And then anything above that is H, is H final, final height. Okay, so like I said, conservative and non-conservative forces lead to conservation of energy. Just if you know the difference between them, or if you at least know that the main one that messes things up as far as conservation of energy goes is friction, then you're good. If you see something say, ignore friction, and it looks like an energy related problem, that is absolutely screaming conservation of energy at you. If you see a collision problem and it says nothing about friction or it says ignore friction, that is screaming conservation of momentum. And when I say conservation of energy, I specifically mean something just like this, where you set up conservation of energy, you decide if any terms are zero, and then you solve for whatever's left over. That is chapter 6's version of the draw a free body diagram, fill it in, fill in the tables, add up the net force in the X and Y directions, all that stuff. This is your structure you follow for conservation of energy. You have KE plus PE equals KE plus PE, initial equals final, and then decide if anything's zero, solve for what you want to know. So these examples are two perfectly good ones to do that. On a conceptual level, the only important thing is that this only works if, like we said, non-conservative forces do zero work. That's the thing that makes energy be conserved in a system is if non-conservative forces like friction, things that are taking energy away from your system, from taking money away from it, are not there to do that. That's how you hold on to all your money, how you conserve it. So derivation stuff is out. And then here, just definition of conservative versus non-conservative is the most important stuff on this page. Hopefully scratching out is not making it more confusing. I'm just trying to kind of limit the stuff you worry yourself about. Applying the work energy theorem in this form of saying like, okay, what if friction did act? How much work did it do? Yeah, don't worry about it. There won't be one that explicitly says something like that of like, well, what actually is it if you account for friction? There could be ones where there's like one on the practice exam where you pull a block and it says, all right, what is its kinetic energy after a certain distance? That's telling you to use work energy theorem because it gave a distance. Power's not on there. Impulse momentum. The most important kind of first step is the impulse momentum theorem. In this form right here, it relates average force. It's the only equation we've ever seen that has average force in it. So if something asks you about the average force, this is the only option you have. That's a good thing. Remember that. But this is how you would find that average net force on something, this impulse momentum theorem, and this right here is an example of it. How we got to the idea of it, all this in between stuff, as far as an exam is concerned, is not critical. But as usual, knowing what momentum is, knowing what impulse is, probably a good idea. Okay, then conceptually, it's good to know when conservation of momentum works. It is when there is no external net force on the system. You don't have to worry so much about the word average there. That's just to agree with the impulse momentum theorem thing above. But external net force, something like friction, something coming from outside of the system we're choosing to look at. And usually our system is the two things that are running into each other or pushing off of each other. And so that would make friction coming from the ground an outside or external force that could change the system's momentum. So if you see a problem saying ignore friction, but things are colliding, you don't want to use impulse momentum theorem. You want to jump straight to conservation of momentum in that form right there. Okay, so again, concepts, know when conservation of momentum applies, but calculation, know how to apply conservation of momentum, which these examples are really on par with what could show up on an exam, very similar to what could. We already said the stuff about the ballistic pendulum is not anything to be worried about, and then 2D collisions are not. Another concept related thing is differences between elastic, inelastic, and completely inelastic is a type of inelastic collision. So mainly between elastic and inelastic. The differentiating feature of those collisions is the kinetic energy of the system, how much you have left over after the collision. If you have the same amount as you started with for the system, that means you didn't lose any. That means it was conserved. We say that's an elastic collision. If you have, so that's no kinetic energy loss. If you have some loss, that's an inelastic collision. And then for the elastic collision, maybe the only other thing to note is that the kinetic energy was not lost doesn't mean that it didn't get redistributed. So during the collision, I don't know, car A had a certain kinetic energy, car B had a certain kinetic energy, their total was a certain value. If it's an elastic collision, that total has the same value after, but car A may have more kinetic energy than it had before, and car B may have less. It just depends how that total kinetic energy got redistributed in the same way that the total momentum of your system, the red vector here, doesn't change, but how much of it is the momentum of one object versus the momentum of the other can change. It gets transferred, handed off from one to the other. Okay, that is my quick recap of chapters end of 4 up through 5, 6, and 7. So for anyone who is currently here, do you have questions on things you want to look at? We'll start with that. Okay, then I will, I got a couple over email, so I'll take a look at those first, but for all of these, I'm not going to go through the whole solution. I'm going to show how to set up the problem up into the point where you have to do some algebra to get to the answer. So let's see, this is the blank one. So questions 14 and 16, I think I was emailed about. So we got a satellite in orbit. It has a certain radius, we call it R, a certain mass. The mission is to observe the climate from an altitude of that distance right there. So one thing I need to remember is altitude, how far above the surface I am. That's the thing that's 4.88 times 10 to the 5. And then the radius is the total distance, that R is that distance right there, is 3.397. Oh, nope, that is incorrect. That is not my total distance. It says Mars has a radius of that, so maybe more appropriate to call that capital RM. It's saying this right here is 3.397 times 10 to the 6 meters. So my total distance from the satellite to the center of Mars is that distance RM plus this altitude. That will give me R. Okay, is that even what 14 is asking about? No, it's asking about which arrow gives the direction of the net force. The satellite is moving in a circle. Only one type of force moves things in a circle. It's a centripetal force. That just means a force that makes something move in a circle, more or less. And so I have to remember, all right, what do centripetal forces do? It's in the name. Centripetal is center seeking. They point towards the center of the orbit, which is the center of Mars. So the direction of the net force is to the right. 16, I did mention PHYS is not super critical for this, but there is this formula that's on the sheet up above. It's just we replace the mass with the mass of Mars, and then remember that this radius R is not just the altitude, but that along with the Mars radius. I'm writing the radius right now, so I need to add the altitude to that. 10 to the 5, whatever, up to the 3/2 power, square root of gravitational constant, 6 point, blah, 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 blah. And then the mass of Mars, 6.4 times, again, blah, 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 blah. You will get to the answer from that. Okay, so that's 14 and 16. Oh, okay, it was 15 that I needed to look at. So orbital speed. Very similar. We have a relation for orbital speeds of v speed. And then this total distance r radius, if I know the mass m of Mars, it's square root of g in Mars over that radial distance. I replace the mass of Earth with the mass of whatever's being orbited, in this case Mars. That'll be 6 points, mass of Mars that's given up above. And then again, what I get from adding these two terms, the height and the radius, or the altitude, and then the radius of Mars, I add those together. 3.39, whatever, plus 4.88, whatever. That's all under the square root in this. So that's 15. There were questions about 4 or 6, chapter 4. Okay. I'll start with 4. 6 is more involved, but it's the same process. So I'm going to do 4 in a little bit more detail, and then 6 I'll do as a very fast. It's like this, but these are your extra things going on. So before I want to know magnitude of normal force, I don't really care. I want to fill in my table before I'm concerned about what I want to find. So to do that, I need to, if I haven't drawn a picture and it's not given, I should draw a picture. Here I've got one. So now I just figure out if I've got all my forces there. I don't, I need the weight, or that's mg. I need to make a free body diagram. Those are my forces acting. To finish my free body diagram, I need axes. So I'll do the usual thing we do for ramps of having my axes like that. I will say, okay, I know the ramp has an angle of theta. That means that the angle between the ramp surface and my weight vector is 90 minus theta. That means compared to this axis going through the normal force angle, that angle is going to be theta. So that's theta. This is 90 minus theta over here. I start making my table. Weight. I look at which of those go in the positive X and Y directions, which we usually call to the right. In this case, it's sort of down to the right, positive X, and then upward away from the ramp, positive Y. So the normal force has no X component based on those axes, 0, similar with the, nope, that's it. But it does have a Y component of positive, whatever the magnitude of that force is, whatever its size is. Fs, static friction, it is purely along the x-axis, it points in the negative x direction, so it's that size. And then normal, or Fs has no y component, so that's 0. Okay, weight, I need to break it into components, so I need to come back to my free body diagram and draw in components. I'll say how much it goes along the y-axis, how much it goes along the x. I could have drawn that not just this way, I could have drawn it this way over here if I wanted to. It's the same 2 components, it's just which side of the triangle I choose to draw them on makes it more clear which angles I should use and whether to use sine or cosine. So if this is my opposite one, W, it's going to be Wx is my x component there, Wy. I can say, if I'm not sure whether to use sine or cosine, right, I just look at my angle there, sine of theta. I look at what's opposite it, I see Wx. I look at what is the hypotenuse, that is the weight, so mg or just the magnitude W, whatever symbols you want to use to talk about it. Cosine theta, I look at what's adjacent to that angle theta, I see Wy. I look at what's the hypotenuse, that is again the length of my overall weight vector, magnitude mg. And so Wx is going to be mg sine theta. Wy is going to be mg cosine theta. So I also need to make sure I've got directions on this right. So Wx is in the positive x direction. Wy is in the negative y direction. And it's going to be positive mg sine theta, negative mg cosine theta. Okay, that's all my forces and all their components. I'm finding my net force. To do that, I add down each of these columns to get the net force in the X and in the Y. So in the X, I get mg sine theta minus Fs. In the Y, I get Fn minus mg cosine theta. I, because of Newton's second law, can set that equal to max and may. I now decide, do I have an acceleration in the X and Y directions? My car is not accelerating down or up the ramp because it's parked. So the X acceleration is 0. The Y acceleration is also 0 because the car is not flying off away from the ramp or shooting down into it. It's just sitting there. So I'm left with the two equations, mg sine theta minus Fs equals, I would have put m times ax if that were still there, but we said that's 0. Fn minus mg cosine theta. Would have put may here, but we said it was 0. Okay, I've not kind of taken my head up above water one moment since I read this problem to see what it's asking for. Now I'm ready to do that. It wants the magnitude of the normal force. Oh, look, I've had my head down this whole time. I've got these two nice equations that really summarize a lot for me. The second one says the size of the normal force is mg cosine theta. I know m is 2000, and mg is 9.8, theta is 30 degrees, so that's going to give me a certain number. Okay, so I get to number 5. Oh wow, I'm already done with number 5 because I already did all this work. What is the magnitude of the static frictional force? Well, I said mg sine theta minus Fs equals 0, so Fs equals mg sine theta. 2,000 kilograms times 9.8 times sine of 30. You may tell yourself this takes a while. It's a long process, and it is. It gets shorter with practice for one, but two, having a long process that works every time is a whole lot better than shooting in the dark and maybe finding a shortcut. So if this stuff is still not quite clicking, try to follow this process. Try and fill in what you can. Don't erase stuff. Just do what you can. Okay, number 6. Like I said, I'm going to kind of breeze through this. So I think about what forces are acting. I've got friction because it's telling me a coefficient for it. Okay, telling me an acceleration up the ramp, ax. It's telling me a mass, 200 kilograms. It's pulled up the ramp. That might be relevant. By means of a rope parallel to the surface. The ramp is at 30 degrees. That's theta. With respect to the horizontal, coefficient of static friction are labeled. All right, find the tension. Find T for this rope. So now that I've labeled some stuff, I'm going to finish drawing all my forces in my picture, turn that into a free body diagram, follow the same process. Weight acting down, normal force perpendicular to the ramp. Friction is going to oppose the sliding of the log, so it's going to act down the ramp. It's kinetic. Okay, looks like I'm ready to make a free body diagram of all my forces. I have tension, normal force, kinetic friction, weight, and I need X and Y axes. Friction and tension are along the same axis because they're along the ramp, even though my free body diagram is not really making that clear. And then normal force is perpendicular to the ramp. So if I draw my axes like that, I'm going to get 3 out of my 4 forces on an axis. All right, now I have my free body diagram. I'm ready to make the table. Force, X component, Y component, Fn, Fk, C, G. Okay, quickly go through this. So my x 0, my y is positive x, and my x component to this negative fk. This is 0. For tension is plus t, y equals 0, mg. It's going to be mg sine of theta. X in the negative direction, mg cosine theta. And in this case, it is also in the negative direction. That would be because my two components look like this. That's wy, or the y component. This is wx. So it's in the negative x and negative y directions. You have a negative for both. How I got sine and cosine is the same way as in this problem up here. I just jumped a couple steps just to keep it a little bit shorter, but you can follow the exact same process we did up here to get that, and I would recommend it. Now look at net forces. I have T minus Fk minus mg sine theta. That's my net force in the x direction, so max. Then this Fn minus mg cosine theta. That's my net force in the y direction, may. I decide, do I have accelerations? I do in the x direction. So this cannot be set to 0, but I don't in the y direction because the log is still not leaving the surface of the ramp. It's not moving away from or towards it. It's not accelerating by gaining velocity in either of those directions. So I still see Fn equals mg cosine theta. I don't know if that's helpful, but it is true. Okay, now I'm at a stage where I look at what I have to find tension. This equation right here has tension. I'm going to jump down into this margin down here. So that equation tells me Fk plus mg sine theta. And whoops, plus max. So I'm moving everything that's not tension over to one side. So if I have all three of these things, I'm done. I know m, I know g, I know theta is 30 degrees. I know x acceleration. I know that mass. So the only thing I got to be a little bit careful about is kinetic friction. I know that the magnitude of it is mu k Fn. That's a substitution I can always make for kinetic friction, just like I can always say mg for weight. So now I look at that. Do I know mu k, the coefficient of kinetic friction? Yes, I do. It's given, it's 0.8. Do I know Fn? I do from my other equation. It's mg cosine theta. So in total, T equals mu k Fn for this Fk piece. Fn is mg cosine theta plus mg sine theta plus max. And I know all of those things, so I have, for all intents and purposes, solved the problem. That one's more involved, but it's the same process. And again, I didn't care what I was solving for until I followed that process. That's just me trying to really set that and send that home. If you don't know the shortcuts, if you're not comfortable making the shortcuts, don't make them. I honestly don't do these problems like this in my head. I have to think about it. I would actually say like T minus Fk minus mg sine theta equals max. I'm just seeing it from a picture. And Fn minus mg cosine theta equals 0. I have done these problems so many times that I just kind of see it. But it's okay not to. And if you don't follow this process, please. I said, if you don't see the shortcuts, please follow this process. Just be clear. Okay, let's see, what other questions? Chapter 5, 13 or 16. The one better we'll do, we already did 16, so let's do 13. What is the magnitude of the frictional force between the tires and the road as the Jeep negotiates the curve? So the Jeep's going around a curve. I should probably look at the original statement for the problem first. Let's see, a mass along a straight 500-meter portion. I don't necessarily know what to label that. Maybe it's a distance, maybe it's X, I don't know. From A to B. Okay, so that's up here. If I'm not given a picture, this is the picture I should be drawing already. at a constant speed of 10 meters per second. So I should be adding that if I didn't have a picture. At B, this Jeep encounters an unbanked curve, so flat road, radius 50 meters. I should be labeling that if it was not already given. It follows that road from B to C, still at that speed of 10 meters per second, but I know that that means it's going 10 meters per second that way. When it's at that point in the curve, then it's this way. So we can negotiate the curve, and finally at the end, it's actually going the direction that's on the other side of this curve. So we'll be going south now. Okay. So what is the magnitude of the frictional force between the tires and the road? Normally, to solve something like that, I would be drawing a free body diagram, looking at my tables. But here, I'm seeing this rotational piece. So, I mean, if I wanted to do that, I could, and I could think of the free body diagram for the car. If I'm looking at a side view on the tires, it's something like this. Static friction. There's the weight of the car. There's the normal force. But this is me taking a different kind of view of the car as it's going through this curve. So to orient ourselves, this would be what I'm calling the direction of static friction as it's going around the curve. And so in this picture I've drawn down here, it's like the car is coming out of the screen at me. This is like the windshield of the car. Okay, so if I wanted to look at it that way, I would look at my forces in the x and y directions. I would end up saying the net force in the x direction is negative Fs, because it's to the left, and that equals mass times centripetal acceleration. The centripetal acceleration is also to the left. This wouldn't go on the free body diagram, but I'm just kind of making a note of it. In my picture up here, it is also towards the center of that curve. Should have used a different color. Oh well. So I need to replace that x acceleration with the size of the centripetal acceleration, v squared over r, but it's negative. So I'm left with the equation negative Fs equals negative mv squared over r. The negatives cancel. The magnitude of the frictional force is mass times v squared over radius. And I have all of those things. It's 1800 mass. The radius is 50 meters. That's r. And the speed v was 10 meters per second. So that answers that one. If I put all those things in. Okay. Let's see. One of the others, chapter 6, 21 or 24. Okay, chapter 6, work and energy related things. So I should be thinking about those work and energy type things as I'm approaching this. And again, these exams are in order by chapter. So if you're about 3/4, 2/3 of the way in, that's probably what you want to be thinking about too. Concrete block with a mass of 10 kilograms. So that's a mass. Label that on here as well. Pulled 7 meters. That's a distance or a size of displacement, magnitude of displacement. Pulled over here. 7 meters. By means of a rope. The tension in the rope is 40 newtons. So the size of this force, 40 newtons. And the net work done, so this is the net work done, W net. I guess I should have written it over here. W net is 247 joules. We want to know the angle the rope makes with the horizontal. So we want to know theta. Okay, I've got things about work. I've got things about force, tension. I've got things about mass and distance, or just the size of a displacement. So if I'm not sure what to use, I come back up here I look at the chapter 6 related stuff. I say, oh, well, that looks like it's got some of those things. As force, I need to know that this is where I should put the size of that tension. That's force. This is where I should put that distance or displacement. And that's going to give me that angle theta. This is the only one I see that actually has theta in it. The only thing I have to be careful about is this just says work. The work done by one force. It said it told me net work. Why is that okay? To find the net work on something, we look at the work done by each individual force. Tension is one of them, but we've also got normal force, we've got weight, and I need to think about those if I'm being fully honest, technical about it, I guess, in order to talk about the network. But the thing is, the conceptual thing, normal force is perpendicular to that displacement. So is weight. So each of those is going to do zero work over this displacement. Tension is the only thing that does work. And so I can take that W net and use it for the work being done here. Use it for that F cosine theta B thing here. And if I do that, I will get that theta is work divided by force and distance. And we take the inverse cosine. Just skimming through some algebra. Inverse cosine of work is 247. Oh, 247. Over the force, which was the force of tension, 40 newtons. Distance, 7 meters. And we get whatever we get from that. Okay, so that's 21. 24 is the next question. Okay, roller coaster starts from rest at the top of a hill. I'm still in the energy chapter, but it tells me I'm going to neglect friction. So if I'm reading this step by step, I wouldn't be at that part yet. So maybe let's do that and read step by step. Starts from rest at the top of an 18-meter hill. 18 meters is a height, and it says it starts there, so maybe that's an initial height. If this picture were not given, I should be drawing it right now. The car travels to the bottom of the hill. Okay, bottom of the hill. Sounds like we are at the lowest point we could be. 0 meters. Continues up the next hill that is 10 meters high. Oh, maybe I was wrong about that last part. I got to update one of them. So it didn't stop at the bottom of the hill, didn't end the problem at the bottom of the hill. It ended up at the other hill. So really my final height should be 10 meters. Okay, now I get to this neglecting friction bit. And I missed from rest. That's an important thing. So its initial speed is 0 meters per second. And now I get to neglecting friction. How does that help me? Well, if I wasn't thinking it after labeling this stuff, I should be thinking conservation of energy. It relates heights and speeds through that kinetic and potential energy relationship. So I need to check, is that okay to use here? And the answer is if any non-conservative forces are doing work, it is not okay to use conservation of energy. It is not conserved for that system. But if a non-conservative force is doing, or excuse me, is not doing work, it is okay to use it. So the fact that it told me to neglect friction is screaming, it is okay to use conservation of energy. The main big bad non-conservative force is not doing any work here. There is that kind of more subtle one of the, oh, where'd they go? Of the normal force, but it is always going to be perpendicular to the direction this thing moves. Because it's always moving along the surface, whereas normal force is always perpendicular. Should not have a vector hat right there. Should have it up here. Okay, so there are no non-conservative forces doing work on the whole car, so energy is conserved. I don't remember my conservation of energy equation. Nowadays, it actually is burned into my brain, so I do, but I come back up here. If mechanical energy, E, is conserved, it says use this. This is conservation of mechanical energy. And it says initial potential energy plus kinetic is initial plus final potential energy plus kinetic. So energy H0 plus 1/2 energy GHF plus 1/2 BF squared. I have a good bit of this stuff. I have H0. I have V0. It is 0. I have HF. I want to know, how fast is the car moving? What is its final speed after all this happens? So this, without the square, is what I want to know. I know almost everything else because energy is not domain, but I don't know maths. And so I have to say, is there anything I can do about that to make it not a problem? The answer is yes, because it's in every term. I divide both sides of the equation by m, whatever it is. If it's 50, I'm dividing both sides by 50. It's going to get rid of that multiplication of mass in every term. So I'm left with GH0 plus 1/2 V0 squared equals GHF plus 1/2 VF squared. Okay, can I simplify even more before I try and do the algebra? Yes, the initial speed was 0, so this whole term is gone. Let's start from rest. All right, so now I'm left with solving GH0 equals GHF plus 1/2 VF squared. If I solve for VF, I'm going to gloss over the algebra, but I need to get rid of everything except it, get it on its own. I will end up with 2G H0 minus HF. Take a square root, that's what's going to give me VF. If you got this far and then you got lost in the algebra, that would be 9 out of 10 points or 8 out of 10 or something very close to full credit. Okay, let's see. 36 or 38. We'll again set up both, but not fully solve. 1,000 kilogram car traveling east at 20 meters per second. I'm this far in the problem, I should already be drawing something. Car. Terrible car, doesn't matter, it's okay. 20 meters per second to the east has a mass of 1,000 kilograms. We use M for mass. Collides with a 1,500 kilogram car traveling west. Okay. 1,500 kilograms. Traveling west at 10 meters per second. Okay, I use mass for that too, but now I've got two of them. Maybe I'll start calling this one N1, this one N2. Since that one was N1, this should be V1. Okay, traveling west at 10 meters per second, that should be V2. The cars stick together after the collision. Oh, I've got a collision. I'm starting to see maybe some conservation of momentum. Does it say ignore friction? No, probably should. But here we can say if it's a very short duration of collision, friction cannot do very much during it. And so momentum is conserved during and immediately after the collision. Okay, so if it's a collision, I need to think about initial velocities and final velocities. It says they stick together. That tells me the final velocities are the same. So it's called the same thing, VF. What is that VF? That's what it wants to know. After the collision. So this is before. And it says find it per after. All right, they're stuck together. just looking at it, I don't necessarily know which way they're going to go. I'll just guess this way. It's not going to affect anything. It's just a guess. So instead of conservation of momentum, right? Split that off. I use this idea that those are the same final velocities. To say M1 VF plus M2 VF on the right side, or I can factor VF out, get M1 plus M2. I could also get that by just saying I now have this bulk object, these joined cars. That's my thing that's moving after. It has a mass M1 plus M2. It is moving at velocity VF. So if I were talking the velocity vector, it should have an arrow next. But it's a 1D collision, so I can get away with scalar components. Okay, what is the common velocity? VF is M1 V10 plus M2 V20 over M1 plus M2. Just skipping the algebra again. And if you put whatever in, you will get that answer, including the correct sign, assuming you accounted for them correctly here. This was east, so it's a positive velocity. This one was west, it's negative. If you do that, you will get a positive or negative answer, and that will tell you whether the overall motion is to the east or to the west, which car won the collision, I guess. Okay, so that's 36, and I think the last one was 38. All right, a 35 kilogram girl stands to the left of a 43 kilogram boy. I should be drawing a picture already. 35 kilogram girl standing to the left of a 43 kilogram boy. Got a little bit more mass, I'm getting taller. Okay, the boy throws a 0.75 kilogram ice ball to the girl. So he has apparently thrown this ice ball to the girl with a horizontal speed of 6.2 meters per second. So it's saying horizontally 6.2 meters per second speed. What are the velocities of the boy and the girl immediately after the girl catches the ice ball? Okay, so I need to kind of think about what all has happened here. I need to say, before anything happened, the boy was holding an ice ball. Then he throws it, and the girl catches it. Now she's holding it. That's actually two collisions going on. And that's the hint it gives. So really, this is kind of in the middle. The boy first threw the ball. So before this, he was holding it. The girl was just standing there, chilling, doing whatever. Okay, and then this happened. So the boy threw it. All right, after that, the ball reaches the girl. She catches it. The boy, as a result of throwing that ball, is already sliding away, doing something. I'll figure out what exactly he did as I go through the problem. But the girl now catches the ball. And as a result of that, she's going to move because they're on ice, they're free to move. Friction is not playing a role here. We expect momentum to be conserved because an external force is not acting on this system consisting of the boy, the girl, and the ball. It's probably easier, though, to think about it as start with this is my system, boy and the ball, because it's just two objects. Okay, and now for the second half of the problem, once I figure out what the boy's doing, I can jump over to this is my system, the girl and the ball, and then she catches it. Okay, so for the boy, that's all we're interested in right now, because he threw the ball first. That's the first collision that happened. Let's say M1 V10 plus M2 V20 equals M1 V1F plus M2 V2F. I just got to figure out what's what. So since I said I'm going to start with the boy, maybe I should have called that M1. If I mislabeled the first time, just erase, change it. Okay, they are standing there. So that means, all right, he has mass m1 of 42 kilograms. His initial velocity is 0. If he's just standing there, so is the ball is just sitting there. So V20 is also 0. And we know the mass of the ball, say m2, it's 0.75 kilograms. Okay, so if we look at what we know here, we know masses. We know that V10 and V20 are both 0. They're just sitting there, the boy and the ball are before throwing the ball. So this is 0, this is 0. On the right-hand side, we don't know the final velocity of the ball or of the boy. Uh-oh. I've gotten to a point where I don't really know what I can do. I've got 2 unknowns. I don't see anything else I can do. Oh, wait, there's this whole other second part. Okay, so I've run out of options. Maybe I try out the second part. Whatever speed the ball has when it reaches the girl is the speed it had when the boy threw it, if we can assume that speed does not change very much over the course of this throw. That's kind of another leap here, kind of a thing that should be stated, but is not. So if I can assume that that speed is constant in between the boy throwing the ball and the girl catching it for that ball, then I can get away with this. By now looking at the girl and saying, all right, M1V10 plus M2V20 equals M1V1F plus M2V2F. But now my initial state is just before the girl catches the ball. I'll re-highlight in green. That's my system, the girl and the ball, and this is their state before the collision. And then after. These are what I'm talking about, initial and final now. So initially, if we still call the ball M2, but now we call the girl M1, call the ball M2, girl M1. The girl's initial velocity is 0. She's just standing there, so her initial momentum is 0. And so we just need to figure out what's going on with the rest of this. So the girl and the ball move away together because she's caught it. So M1 plus M2. We just call this VF overall. So I'm left with M2 V20 equals M1 plus M2 VF. And let's see. I throw this 0.75 kilogram ice ball to the girl. All right, where am I at with this? This is going to be the initial ball speed. This is the ball's mass. And then girl's mass and ball's mass together. That's going to give me VF. So what can I do from there? That's going to be my final thing for that. Make sure I didn't throw something out here. Girl catches the ball and then slides off. They slide off together. That is going to be final speed. And it's going to be V20 equals M1 plus M2. Oh, that's exactly what I'm missing. Got a little bit caught up in the weeds here. This 6.2 meters per second, I have not done anything with. I've not put anywhere. The masses I've kind of labeled as where they go. I actually know what what V20 is, if I assume that it stayed the same through this whole process. It's the speed that the ball reaches the girl at, and so it is 6.2 meters per second. This is not an unknown. What is the unknown is the final speed of the girl and the ball together. And similar up here, V2F, as far as the first collision, is what we would call 6.2 meters per second. All of these are also to the left, though, so I'm going to have to make a negative. And if I do all of that, I should get to the right answer for this stuff. So I would get for the girl, M2 V20 over M1 plus M2 is going to give me VF. That's the common speed of the girl and the ball. And for V20, that's what I'm saying. I'm going to make negative 6.2 meters per second and then put all the mass stuff in. For the boy, our momentum equation was, I'm looking at this one up at the top, 0 equals M1 V1F plus M2 V2F. And this V2F is what we know to be negative 6.2 meters per second. It's the final velocity of the ball after he has thrown it. And so we can find his final speed, V1F, as I solve this for V1F, I get negative M2 V2F over M1. Which looks good to me because I'm expecting the boys' velocity to be positive to the right. And this thing is going to give me a positive answer because V2F is negative. It's negative 6.2. So a roll will get plus or to the right. Okay, so that is how I'm going to get my two answers. This one is more involved. If it were a problem, it would be a two-parter of find the first speed, find the second, so you don't get caught up like I did in that intermediate space and that it gives that velocity. But we salvaged it, and it was just by kind of saying, I should be able to solve this. There should be enough information. And if you just kind of reread what you're given a few times, you will find that missing gap. Thankfully, I did at least. All right, 6:19, so almost a good time to stop anyway. But are there final questions from anyone who is present? Which looks like Savannah.
I had a question on number 2. Would
Okay.
you use the normal force mg equation and divide? Because when I was doing it, I didn't get it exactly.
So, you did the table first. Did you set up all that in your table?
No, I did an equation, Fn over friction divided by kinetic, or coefficient of kinetic.
Okay. So do you know where you got that one from?
I looked it up, and I guess it didn't get me exactly where I needed to be.
Yeah, so did you follow the process of solving for the forces and seeing what was maybe helpful?
I tried to like draw a diagram, and so that was kind of helpful, but I guess it just didn't work out.
So let's fill in the rest of this real fast. Fn it has no x component, it's up. Kinetic friction is negative F, so to the left, 0. This push is to the right, so positive P, 0 y component. And then mg, the weight is no x component, it is down. I look at the net force, and then jump into this next space a little bit, but net force in the x direction, it's going to be P minus F. Over for this next one, it's going to be Fn minus mg. I'm just adding down the columns, adding down the rows, I guess. this first one is equal to the mass times the x acceleration. Second is equal to mass times y acceleration. And so now I look back at what I'm given. It is pulled at a constant speed along the surface. It's not leaving the surface. So that tells me for the x direction, because of that constant speed bit, that there is no horizontal acceleration. This part that it is along the surface, it's not leaving the surface or getting closer to it, tells me this is 0. So I'm left with the two equations, P minus F equals 0, Fn minus mg equals 0. This would be the appropriate way to get to the answer for 1. The magnitude of Fn is mg. Because of this second equation right here, it says Fn equals mg. But like this says, that's not always the case. You only find that out by following this process, going consistently through all your forces. Okay, now we look at problem 2. We say, okay, it gives kinetic friction and the magnitude of the frictional force F. So it is sliding, it is a kinetic friction, so we could write that if we wanted. And we look over here. We say, well, I know that it's equal to that pushing force, but it doesn't tell me the pushing force, so that's not super helpful. But we could use that substitution like we do with weight, but we have this one for friction. We can substitute it out for kinetic friction times normal force. And then to know how to calculate this, it's mu k times mg, because Fn in this case is equal to the weight in magnitude. They're in opposite directions, the normal force and the weight are, but the sizes of them are equal because the block is not leaving or moving towards the surface of this thing. It's in equilibrium. And so I notice, oh, but this is my weight right here. And so I'm treating that whole thing as my unknown. So if I solve for it, I say mg is fk over uk. It should be 80 over 0.3. So I think that's what you said earlier, but we can get to it by just kind of following all these pieces, all these breadcrumbs. Now, does this agree with the answer that's given? And whatever 80 over 0.3 is, I think it's like 267.
Yes. That's what I
That's what you did?
yeah. I just didn't understand why it was like rounded up a few times. So I was just confused.
Okay, so this is not me getting on to you, by the way. This is just saying you really can, for almost any problem with forces, get to the answer by just following this. And then if it really didn't get you to the answer, which this one kind of had a couple extra steps, it means that you've done most of the work to show all the things that don't work. And there's just one little hidden sneaky equation that could answer it for you. By exhausting those possibilities by doing this process. That's another way to eliminate other ways that things could go wrong. So I just really recommend, and this is anyone who's watching this, anyone who's listening, no matter what the problem is, if it's about forces, do this. You will have time to, because you will have a systematic thing you're doing rather than shooting in the dark. That's what makes you run out of time, because you don't realize you're trying different stuff for 20 minutes rather than this systematic process. You know what the next step is, assuming you've written it down. Okay. Did you have any other questions, Savannah?
No, that's all I had. Thank you.
Mm-hmm. All right, well then this is a good place to stop this. I still have to do some finishing up of the exam, but as far as the review, it'll be posted in just a little bit, and I will see everyone on Monday. Just email if there are any questions over the weekend. All right, you have a good day, Savannah.
Thank you.
Mhm.